All right, welcome back everyone. Okay, now this is the further maths paper 2. I try to prepare this video for my students who are going to sit for the exam on Wednesday. All right. First of all, before I start with this solutions or this video referencing here, I would like to wish all my students who are taking further maths best of luck. All right. Now, this paper that I'm trying to prepare for your reference is it's extracted from June 2021, paper 23, as requested by some of you. All right. I'll try my best to go through all the questions in this section here. All right. Okay, let's get started with this. The first question here is complex number. Now find A and B such that the complex number on the left hand side satisfy the complex number on the right hand side. All right, now that should not be any problem at all. This is mainly just a comparison. So I'm going to rewrite this again. We can consider the expression on the right hand side. I'm going to expand that as usual. So we have z phi minus a. And then there you have it. All right. Just to check, you should have four terms here because there are four sort of variables in the factor itself. Right? And then by comparison, we can write this side by side. I'm going to rewrite this again. Z8 minus I Z phi plus I. All right, now you can see that every single term, the coefficient for the complex number z is the same. All right, and then the coefficient for complex number z5 here must be the same as b. Therefore, we can conclude that b must be the same as I here. Okay, that is very obvious. And then next, if you like to compare A, all right, now we can say that by comparing the coefficient for z cubed, we know that A must be equal to 1 here. And then basically that's all we have. And then finally, of course, in exam, it's always good for checking. Like for checking wise, the AB is just A multiplied by I. We notice that is the same as the last term. And then that complete our confirmations that A must be equal to 1 and then B must be equal to I there. So I hope that is clear. It's just 1 mark. You don't have to do anything bizarre in this case. All right. Okay, now that is our first question here. And then for B, we are going to make use of our result of factorization in the first section A by providing the roots for this polynomial complex equation here. And then we need to give the answer in the form of r exponential I theta, which is the Euler form. And then furthermore, you have to make sure that the r, which is the magnitude of the complex number, must be positive. The theta must lie within 360 degree, and then excluding 360 degree. All right. Now, how would that look like? Basically, we know that. Okay. Let me clean up this one. I'm going to rewrite over here so that we can refer to that. So z phi minus 1, and then this one will be z3 minus I. Okay. Let me clean up all this here. Okay, let's continue on with this. Now, of course, I need to clarify one thing here. The z complex number. So therefore, z can be written in the form of r exponential I theta there. That's our intentions here. And then satisfying the magnitude and the argument here. Now for this equation to be true, it must mean that z phi, we are looking at b now, it must means that z phi minus 1, z cubed minus I must be equal to 0. All right, now you can see that these are the factors for this polynomial complex equation. Therefore, this factor must satisfy this equation here. All right. Now from here, we found that z phi must be equal to 1, or it could mean that z cubed is equal to I here. Okay, now that is very obvious. Now from here, we are going to describe. Now, in the exam, it's always a good practice to rewrite this in the complex form because we know that z is a complex number. All right, now z is a complex number here. Therefore, it's always best to rewrite in the complex form. And then once you have done that, it's always good to draw the Argand diagram. Even though it's not a must, but it's always good to draw the Argand diagram to represent this complex number, which is somewhere here. This is imaginary, and then this is the real parts here, and then that is 1 unit long. And then we know that the argument must be equal to 0 degree radian in this case. Right? And then next, we're going to represent this rectangular complex form in its Euler format. So first of all, always check the magnitude is 1 unit long. So therefore, it can be written as 1 unit long as its magnitude r, and then exponential. Now, its argument is 0. Therefore, we can always write down I 0. Now, that 0 just gives us the first solutions. And then we know that we can rotate 360 degree. Now, take for instance, if we rotate 360 degree, you will come back to the same argument again. And then that is also another solutions to the complex equation here. And therefore, because of that, we can add up 2k pi, where here I specifically mentioned that k is having an integer value from 0, 1, 2, 3, 4, and 1, 2, 3, 4 until 4, because there are 5 roots over here. All right. Now let me clean up this part first. We will consider that later. Okay, and then there you have it. Now, of course, to write neatly, we have exponential I 2k pi. Okay, and then if you wish to list this down so that it satisfies all these requirements, then before that, because we are interested to get the complex number z, not z phi, so always remind yourself z will be equal to, we can apply the index rule by applying the root 5. Okay, so root 5 basically means 2k pi over 5 here. Okay, now that would complete our complex number. And then if you wish to list it out, then therefore it will be starting from 0. So 0, that must be 0 then, which you know very well. One of the root is a 1. And then after that, you have a 1 here. So that'll be 2 pi 5. Always check that whether the argument actually found within this given domain. Yeah, it is. And then after that, you have your I 4 pi over 5. And then after that, you have your, is it 2, 3? Oh yeah, 6. 6 pi over 5. And then after that, you have your 8 pi over 5. And then always check whether it still fall within that domain. Yes, it still fall within that domain. And then therefore, you can rewrite this as whereby this is basically just a 1, if you wish to write that down. And then there you have it. Those are our 5 roots given by this factor. Okay, now next I'm going to repeat that for the second part, whereby we have z cubed is equal to I here. Now for this, we're going to apply the Argand diagram as what we did just now. I'm going to maybe draw it at the side here. You can see that this I here is basically, now let me clean this up here. Now basically it's 0 plus I. Now 0 plus I referring to here, 1 unit long. This is imaginary. And then this part here is real. Okay, now that is 1 unit long. And then we know that the argument is measured from here. That must be pi over 2, which is 90 degree in this case. And then therefore we can represent this in its Euler form. We still know that the magnitude is 1 unit long. Therefore we can rewrite this as Z3 as E I pi over 2. And then don't forget, because we can repeat that for one complete cycle, therefore we can write down 2 pi here. And then there you have it. That is the second general solutions to this factor here. And then we can simplify this so that we can get z instead. Now divide by 3, there will be a 6. Okay, and then making the k, you must specify the k starting from 0, 1, and 2 because we have 3 roots here. And then therefore from here, I'm going to put the divider here. Alright, therefore we can conclude that the z would be when k is equal to 0, we have ei pi over 6, that's one of them. And then when k is equal to 1, then, right, now when k is equal to 1, we will have ei phi pi over 6 here. Let me check one more time if I got it correct. Yep, so that is 5 pi over 6. And then lastly, we have another one when k is equal to 2. So that will be a 4, 8, 9. So that will be I 3 pi over 2 here. And then at the same time, you have to check whether all these arguments still fall within this domain. Yes, they are. And then there you have it, the complete roots. So I'm going to list down all the roots. Therefore, we are going to conclude that all the roots are, in this case, will be 1. And then we have like here, this is 0.4. This is 0.1 something. So maybe I'll list them down according to the um, argument there. If you don't want, you can just list them as it is, right? So this one is 0.1 something. So I'm going to list it down as I pi over 6. And then after that, I will have like, I can go for 0.4, 0.8. Yep. Okay, so I'll go for this one here. Let me clean this up here. We don't need this anymore. So therefore, this one will be I 2 pi over 5. And then right after that, we have, let me see here. This is 150 degree. And then this one here is, let me see here, 36 here, so 13 something. So this one will go first, I 4 pi over 5. And then right after that, we'll go with ei 5 pi over 6. And then after that, we will go with the, this is 1.2, 1.5. We're going to go for this one first, I 6 pi over 5. And then after that, we're going to go for this one, 1.5, 1.6. So I 8, oops, sorry, not this one first. It's supposed to be this one first. 3 pi over 2. And then lastly, we will have the other one, which is ei 8 pi over 5 here. And then we're going to count how many are there. We are supposed to have 8 roots here based on the degree. 1, 2, 3, 4, 5, 6, 7, 8. And then there you have it. These are all the 8 roots for this polynomial complex equation. So I hope that is clear. All right. Now yeah, do check out the solution in case I made any mistake. All right. I'm going to move on to the second question shortly. Welcome back. Let's look at the second one. We need to find the McClaurin series for ln cos x, as how my students like to pronounce it, but the correct pronunciations for cos x is hyperbolic cosine x, right? Up to and including the terms in x to the power of 4. Right, that worth 7 marks, but anyway, it's quite worth it in this case. All right, now before we start up, it's always good to make a setup. So I would say that let this be a function. Now, anyway, this method is just to ease our writing, why? So that it looks neat. But anyway, it all depends on your liking, your style. You don't necessarily have to write this as a fx. Okay. Now, based on the Taylor Maclaurin series format, we will have to figure out the value of the function when x is equal to 0, because the Maclaurin series is centered at x equal to 0. All right. So by substitute x equal to 0 here, we will get ln cos 0 here. All right. And then from here, you must be wondering what is cos 0 or cosine hyperbolic 0 in this case. All right. Now, the definitions for cos, just to recap again. All right. Now, definitions for cos x is written as half ex plus negative x here. Therefore, for cos 0, now of course with today's technology, you can just enter it into calculator. It's ridiculous to do this manually, but in case you run out of calculator, for instance, well, this will be a lifesaver for us. At least you know the fundamental. We are going to substitute x as 0. So we know that e0 is a 1. This one is also a 1. And then half of that, that will be a 1. All right. Unfortunately, ln 1 is a 0. Therefore, we can conclude that this first result is a 0 here. All right. So I hope that is clear. All right, at this point. Okay, now that's the first one. Okay. Now from here, we are going to continue on with the second derivative. Of course, the main thing is not the definition of the cos, but it's more like the derivative of this. Okay, now we're going to differentiate this. Now, there are many ways to differentiate this. Of course, the official way is by using substitution and chain rule. Okay, now just to show you how that actually works. Okay, so this part here is just to review here. So take for instance, you let y is equal to ln cos x here. We will let u equal to cosine hyperbolic x, and then if you go through the original steps, the differentiations for this. Now, if you are not very sure of or can't really recall what is the differentiation for hyperbolic cosine, you can always use its original definitions for cosine, which is given as 1 over 2 ex plus e negative x here. And then by differentiating this with respect to its exponential form, you will figure out that that is ex minus e negative x. And then that gives us the definitions for sine hyperbolic, or my student like to pronounce it as shine. Yes, I hope everyone will shine, and then definitely, and then I would say, of course, everyone will shine in this upcoming exam here, right? So from here, this is u. And then once we have done this, we know that the y can be written as ln u now. By differentiating y with respect to u, we have 1 over u. But anyway, even though this question is about u, but don't forget that you need to substitute its original representation of u. That there you go. All right. And then from here, we are going to apply the chain rule. This is where our dy dx come in because we are interested to obtain the dy dx. dy dx is dy du by du dx. And then from there, you have 1 over cos x by du dx. So du dx is sine hyperbolic. And then if you notice that this is sine hyperbolic and cos x, and then that can be simplified into tangent hyperbolic. All right, now I hope that is clear. All of this can be simplified into tangent hyperbolic. Now, there you go. That is the differentiations. That's the first derivative for this function here. And then by repeating the same process again, we are going to find out the first derivative centered at about x equal to 0. So we're going to substitute that tan 0. Right now, at this point of time, tan 0 is sine x over cos x here. Okay, that is the same as half e0 minus negative 0 divided by half ex again. I'm supposed to substitute e0 inside for cos. And then you will notice that the result must be equal to 0 because numerator is 0, and then that will give us a 0. And then there you go. The second term is also 0, which is not very meaningful at this point. All right. Now I'm going to pause here for a while. I'm going to proceed on to the second derivative and then the third derivative, and then we'll see whether we are lucky enough to collect some terms that is significant at this point. All right, we're going to look at the second derivative now. Okay, we can use this result here. Okay, now we're going to differentiate this second time. Of course, you can always refer to your data booklet. Oh yeah, by the way, I forgot to write this. The result is 0. Now we can always refer to your data booklet for the derivative of hyperbolic tangent. But then again, if you forgot about how to do this, you can always apply the definitions of tangent in this case. So just to review one more time, I will always check using its original definition just in case I miss out some of the differentiation that I thought I can remember. All right. So in this case, we know that tangent hyperbolic can be written as half. Okay, now that is our tangent, and then we can simplify everything here as okay, and then there you go. And then I'm interested to perform derivative here. Now I'm going to apply the quotient rule as usual. I will get and then subtract off with and then differentiate this. And then at the end, I need to copy down my denominator square. All right, and then the numerator, of course, you guys can simplify that quite easily. You will notice that this is ex plus e negative x square minus of ex square. Okay, and then you can simplify anyhow you like. You want to expand it, or you can use the difference of square of identity or formula. You can use it. For me, yes, I will use the difference of square identity to simplify this. All right. So the first one, I will have 2e negative x by the second one, I will have 2ex here. All right, you'll notice that at the end of the day, this can be cancelled off, and then that will be a 4ex plus e negative x squared. And then the beautiful thing about this is you can, even though it doesn't look as if you can restructure, but if you can restructure this as, it can be written as 1 over ex plus e negative x over 2 square. And then that would actually give us, we know that the denominator actually represent uh, cosine hyperbolic square. And then that indirectly gives us the definitions for secant square. And then there you go. That is the differentiations for this tangent hyperbolic. Okay, I hope that's clear. You can check that out. Okay, we can rewrite this straight away. And then, of course, to proceed on, we're going to repeat the same procedure by substitute 0 into here. Okay, you can substitute 0 into here, here, and here, of course. Yeah, because at the end of the day, we want to get a numerical number as fast as possible. For instance, in this case, you notice that the answer is actually 1. Therefore, this is a 1. Okay, we can substitute the 0 into the x. We will get a 1 here. Now, just to make sure everyone is clear, I'm going to use the definition here that is the same as 1 over. All right, now you can key into your calculator. That is definitely a 1. And then there you go. That is the second derivative. I need to repeat this process until I get the fourth derivative, because the fourth derivative will give me the coefficients that attach to the term x to the power 4. All right, now I hope that is clear. All right, now I'm going to move on to the third one now. Okay, let me clean this up here. Okay, now the third derivative. Okay, this one we also have to be very mindful here. All right, now just to recap again, or for checking purpose, we know that we are at this point right now, which is secant square x, and then that is exactly the same as this one here. Okay, now I'm going to rewrite that. That's exactly the same as 4, if you wish to write that, ex plus e negative x square. Now, if you like, you can repeat using this definition. For me, I always use the definitions for my differentiation, because this hyperbolic, sine hyperbolic tangent, they are just something like a nickname for that um, definitions of hyperbolic, right? But underneath that nickname, you have the original transcendental function, right? So from here, we can differentiate that as usual. You can apply chain rule, for instance, like for me, I will apply chain rule. Definitely, that will be negative, I would say negative 8. And then I will have, oops, I have more in this case, of course, plus e negative x to the power 3, definitely. And then after that, I'm going to differentiate this using chain rule. I'm going to take a bit of shortcut here. So if you guys are trying out this, you can try on a piece of paper and then check with me whether you get the same one as mine. Okay, this is what I have at this point. So that is my third derivative. If you like, you can keep it as it is, but if you still like to convert it back to the hyperbolic format instead of exponential, you can actually convert it back. So take for instance, in this case, we can actually divide this as negative e x minus e negative x, and then that can be written as e x plus e negative x over 2 to the power of 3 here, if you like to look at it this way. Okay, and then now of course next we can restructure this one more time here by introducing, for instance, I can purposely introduce a half here. Now of course don't forget, anything they introduce we need to pay the price here, so don't forget you need to multiply by 2. All right, now I'm going to take out the -2 straight away because there's a negative here. And then I'm going to write that down as equal to -2. Okay, this is how it looked like, -2. Multiply this, I still get my -1, so that is cool. And then from here, I will have my ex plus e negative x over 2 to the power 3. All right, and then this would automatically become, I'm going to write it down here, this is -2. The numerator is hyperbolic sign. The denominator, of course, you guys know this very well. This is cosine hyperbolic x there. You can actually leave it as it is, or if you like to convert back to secant hyperbolic and sine, you can do so, or tangent in this case. Now, take for instance, we can rewrite this as sine x over cos, and then after that 1 over cos square. And then from here, you will see that this is typically a -2 tangent hyperbolic, and then this is basically a secant square. So the entire thing can be simplified into, take for instance, if you do like this, then you can rewrite this as 2 tan x secant square x. And then of course the last step is, as usual, I need to evaluate my third derivative with the value of x equal to 0. And then I noticed that whenever I substitute 0 into my tangent hyperbolic, it yields a 0. Therefore, if I substitute 0 into here, this would also be a 0. So therefore, you don't really need to waste time to evaluate on the second part here. All right, now I'm going to pause here for a while. Later, I'm going to show you the last derivative. Okay, I hope this is clear. All right, let's take a look at the last part of this differentiation, which is the fourth derivative. Okay, we're going to differentiate this. It looks as if we need to deal with the product rule. Yes, if you are looking at this format, yes, you are going to deal with the products rule. If you are looking at it from the exponential point of view, yes, you still have to apply a lot of like quotient rules and so on and so forth. Right? Of course, there are calculators that can evaluate this directly without any hassle in this case. Right? Now, I'm going to recap one more time how to in differentiate this by using product rule. Okay, so I'm going to rewrite this as y, so 2 now I'm going to differentiate this. I just write down y prime there. It's easier for me to refer to its differentiation. Okay, hold on. Okay, product rule, I'm going to differentiate my tangent. I notice that when I differentiate my tangent, I do get a secant square. So therefore, the first step is I'm going to differentiate my tangent. It will yield secant square. And then by holding my secant square constant, and then therefore I have secant square here. All right, that's how it looked like. And then after that, I'm going to hold my tangent hyperbolic constant, and then I'm going to differentiate the secant square. And then I know that when I differentiate secant square, this is what I have. So all I need to do is copy down. All right. And then after that, I'll try my best to simplify as much as possible. And then that will yield a 4 tangent square secant square. So this is what we have. I would say that this is dy dx for this. Okay, maybe I write down another form. Okay, so that is our dy dx. And then from here, we are going to evaluate. We're going to evaluate this differentiation. Now, before that, I'm going to write down the result of the differentiation. Oops, you can see that when I write tangent, I forgot my h. So it's supposed to be hyperbolic tangent in this case, not the trigonometric tangent. Okay, now I'm going to rewrite that properly. Okay, and then repeating the same procedure again by evaluating this derivative at x equal to 0. We notice that tangent 0 must be 0. And then secant we know that is a 1, so therefore this one will yield a -2 here. And then I hope that is clear. We have already reached the coefficient for the term x to the power 4. All right, now I'm going to pause there. Hopefully you guys are clear with this. I'm going to summarize the result shortly. All right, the last section, which is the conclusion. Now, as a conclusion, we can always write down this fx, which is the original function here, ln cos hyperbolic x, as using the Taylor-Maclaurin's form, is written as f0 here, and then we have the x f1, and then you have your second, and then after that you have the third one, and then we have the fourth term. And of course so on and so forth, but here we just need to list it down up to x to the power 4. Therefore, all I need to do is just extract all the result that I have obtained. I notice that this 2 is not significant at this point, and then I do have a 1 here, and then once I plug it in, I notice that there is x over 2 only, and then I don't have the third term. Okay, I don't have the third term because third term is 0. And then I do have the fourth term. The fourth term is -2. That would yield x4 over 4, -2 here. And then by simplifying this correctly, I would have half x squared. This is definitely negative, -12 x to the power 4. And then there you have it. That is our Maclaurin series for this function, ln of hyperbolic cosine x. I hope that is clear. We're going to move on to the third question shortly. Right, welcome back. This is our third question. It's upper and lower bound using integrations and approximation. Right. Now we are given the diagram that represent a curve given as y equal to x over 2x squared minus 1. The domain given is for x greater than or equal to 1, together with a set of n minus 1 rectangles or unit width. Unit width means 1 unit long as depicted in the diagram. By considering the sum of the area of these rectangles, show that the sum of that series should be less than the expressions given. That's our first part A. And then once we have done that for B, use a similar method to find in terms of n the lower bound for the same series here. Okay, now I hope that is clear. All right, now I'm going to break down these questions into their corresponding sections so that we can solve it section by section. So we're going to start off from A. I'm going to erase out some part of this so that it saves some space for us to write. Okay. All right, let's look at this question here. This is the first part. We're going to prove that the one that I highlighted in the box here, I have already removed the question so that we can concentrate on what we are supposed to do to prove that the sum or the summation of this series should be less than this. All right. What we are looking at is actually the um, upper bound, upper bound for this summation. Right. So by considering the area, all right, now we know that the area under the area, the sum, I would say that let's call this the sum of rectangle under the curve. I will call this be um, AR. So the area of the rectangle under the curve is AR. So therefore, AR can be written as width times height, of course. So basically, we just use a very simple setup here. Is the width multiplied by the height, and then the height. You will notice that the height is actually given by uh, by the by the y coordinates of the curve itself. So here I would label this as function x, for instance. So therefore, the height here can be represented as f2. And then the height for x equal to 3 can be represented as f3. And then as we proceed on to the last part, the height of the last rectangle, of the n rectangle, right, will be given as, or is given as fn here. Now I hope that is clear. And then we're going to use this notation here to represent the area of the rectangle under the curve. Now that will be 1, the width is 1 multiplied by the height. Then the second one, the width is the same, multiplied by f3, and so on and so forth until we reach the last one here, the nth rectangle. Okay, and then there you have it. All right. And then this whole series can be represented using the summation notation, of course. This is written as the sum of, if I start from r equal to 1, oops, sorry, I should not start from r equal to 1 because I noticed that it starts from 2. So therefore, it's supposed to be 2 until n. And then I'm going to put in fr. Fr. Fx is equal to this, therefore Fr must be equal to R over 2R squared minus 1. So the sum go from number 2 until n there. That's what we have, okay, currently. Those are the area. And then we know that this summation here, or this series, must be less than the definite integrations from 1 until n, which actually represent the area under the curve. Right? Now, that must be less than the definite integration from 1 until n for that particular function. So this function has this name here, x over 2x squared minus 1 dx. Now, that is the entry to any problem that involves bounds. Yep. And then once you have done that, you just need to compare what we have at this point. You can check that out that the R actually start from 1, whereas what we have actually start from 2. Uh, that is the one thing that we need to take care of since we don't have that extra term f1. So how can we do this? We can do this by purposely introducing an extra term f1 into the equations there. So we can actually do it this way. We can introduce it. Bear in mind, this actually represents f2. So we can actually introduce one more f1 here. Add up to the left-hand side of the inequality. Must be less than Okay, now that's how it would actually look like at this point. Okay, let me clean up this properly. That is minus 1 here. Right now, I hope that is clear. And then because we introduce this extra term, we can incorporate this term into the series. Instead of starting from 2, we can rewrite this as r starting from 1 until n for this summation. Then that will be less than. All right, then you're wondering what is f1 then. F1 basically is just the height for this line here, or is the y coordinate when x is equal to 1. So all we need to do is just substitute this into this function, and then therefore we found that this is actually a 1. Now there you go. This is the most important concept and setup that we need to achieve first before we even get the proof. All right. Now I'm going to pause here for a while. You guys can go through the fundamental. So make sure the fundamental is correct. What come next is going to be a piece of cheesecake. All right. I'm going to pause here. Later on, I'm going to erase off this fundamental definition. Then we are just going to concentrate at the integration of the functions, the rational function x over 2x squared minus 1. All right, now, all right, welcome back. We are going to complete this proof here. We have reached the section where we derive this from the definitions of the area under the curve and the area that represented by the unit rectangle. All right. Okay, so first of all, I'm going to show you how to obtain the integration. Of course, this is the main section that we're going to tackle with, because once you manage to integrate this, then you will be able to prove that particular inequality. All right, so therefore, we're going to consider this integration here. Now, at this point, you must be wondering what sorts of methods that we can use to integrate this. There's tips that you can follow. Always check for rational functions if there's a difference between the degree of the numerator and the denominator. If there is, especially the denominator is larger than the degree of the numerator, you can always apply integrations using substitution. So therefore, from here, I'm going to consider this integration here. All right, I'm going to put the setup at the side here. I'm going to let you can say let u equal to 2x squared minus 1. Du dx would be 4x then. And then from here, you will notice that, okay, now I can say that x dx, if I arrange the x and dx together, it must be a quarter of du. Anyway, this setup is entirely up to your liking at this point, right? And then once you are ready with this, we are able to substitute this because the numerator is a u. And then the denominator x dx is quarter of du. And then I'm going to drop the boundary first, all right, because later I'm going to replace the u that I'm using here. Okay, so from here we have a quarter of, now you know the integrations for this, which is basically just ln u. And then what is u? Don't forget to replace it back. It's a quarter of ln 2x squared minus 1. Now, once you have done this, because there's a boundary from 1 to n, therefore, it's always best to put back the boundary from 1 until n here. And then we're going to do that by substitute the n first. We have ln 2n squared minus 1 minus ln 1 inside. So this is 2 minus 1, which is a 1. And then at the end of the day, we have 4 ln 2n square minus 1. Okay, and then that is our integrations that we are looking at here. Therefore, we can conclude that from here, we can conclude that the summation 2r square minus 1, summing that from r equal to 1 until n, must be less than quarter of ln 2n square minus 1 plus a 1. And then with a little bit of inspection here, we found that yes, we have done it. That is the proof for the upper bound. I hope that is clear. I'm going to show you the second questions, the second part of this, where we're going to obtain expressions that represent the lower bound. All right, welcome back. We are going to complete this proof here. We have reached the section where we derive this from the definitions of the area under the curve and the area that represented by the unit rectangle. All right. Okay, so first of all, I'm going to show you how to obtain the integration. Of course, this is the main section that we're going to tackle with, because once you manage to integrate this, then you will be able to prove that particular inequality. All right, so therefore, we're going to consider this integration here. Now, at this point, you must be wondering what sorts of methods that we can use to integrate this. There's tips that you can follow. Always check for rational functions if there is a difference between the degree of the numerator and the denominator. If there is, especially the denominator is larger than the degree of the numerator, you can always apply integrations using substitution. So therefore, from here, I'm going to consider this integration here. All right, I'm going to put the set up at the side here. I'm going to let, you can say let u equal to 2x squared minus 1. du dx would be 4x then. And then from here, you will notice that, okay, now I can say that x dx, if I arrange the x and dx together, it must be quarter of du. Anyway, this setup is entirely up to your liking at this point, right? And then once you are ready with this, we are able to substitute this because the numerator is a u. And then the denominator x dx is quarter of du. And then I'm going to drop the boundary first, all right, because later I'm going to replace the u that I'm using here. Okay, so from here we have a quarter of, now you know the integrations for this, which is basically just ln u. And then what is u? Don't forget to replace it back. It's a quarter of ln 2x squared minus 1. Now, once you have done this, because there's a boundary from 1 to n, therefore, it's always best to put back the boundary from 1 until n here. And then we're going to do that by substitute the n first. We have ln 2n squared minus 1 minus ln 1 inside. So this is 2 minus 1, which is a 1. And then at the end of the day, we have 4 ln 2n squared minus 1. Okay, and then that is our integrations that we are looking at here. Therefore, we can conclude that from here, we can conclude that the summation 2r squared minus 1, summing that from r equal to 1 until n, must be less than quarter of ln 2n squared minus 1 plus a 1. And then with a little bit of inspection here, we found that yes, we have done it. That is the proof for the upper bound. I hope that is clear. I'm going to show you the second questions, the second part of this, where we're going to obtain expressions that represent the lower bound. Right, welcome back. We are going to complete this proof here. We have reached the section where we derive this from the definitions of the area under the curve and the area that represented by the unit rectangle. Right? Okay, so first of all, I'm going to show you how to obtain the integration. Of course, this is the main section that we're going to tackle with, because once you manage to integrate this, then you will be able to prove that particular inequality. All right. So therefore, we're going to consider this integration here. Now, at this point, you must be wondering what sorts of methods that we can use to integrate this. There's tips that you can follow. Always check for rational functions if there is a difference between the degree of the numerator and the denominator. If there is, especially the denominator is larger than the degree of the numerator, you can always apply integrations using substitution. So therefore, from here, I'm going to consider this integration here. All right, I'm going to put the setup at the side here. I'm going to let you can say let u equal to 2x squared minus 1. Du dx would be 4x then. And then from here, you will notice that, okay, now I can say that x dx, if I arrange the x and dx together, it must be a quarter of du. Anyway, this setup is entirely up to your liking at this point, right? And then once you are ready with this, we are able to substitute this because the numerator is a u. And then the denominator x dx is quarter of du. And then I'm going to drop the boundary first, right? Because later I'm going to replace the u that I'm using here. Okay, so from here we have a quarter of. Now you know the integrations for this, which is basically just ln u. And then what is u? Don't forget to replace it back. It's a quarter of ln 2x squared minus 1. Now, once you have done this, because there's a boundary from 1 to n, therefore, it's always best to put back the boundary from 1 until n here. And then we're going to do that by substitute the n first. We have ln 2n squared minus 1 minus ln 1 inside. So this is 2 minus 1, which is a 1. And then at the end of the day, we have 4 ln 2n squared minus 1. Okay, and then that is our integrations that we are looking at here. Therefore, we can conclude that from here, we can conclude that the summation 2r squared minus 1, summing that from r equal to 1 until n, must be less than quarter of ln 2n squared minus 1 plus a 1. And then with a little bit of inspection here, we found that yes, we have done it. That is the proof for the upper bound. I hope that is clear. I'm going to show you the second questions, the second part of this, where we're going to obtain expressions that represent the lower bound. All right, welcome back. These are next sections in this past year paper, June 2021, paper 23 here. All right. Now, by considering the binomial expansions for this particular expression and this, where the z represent a complex number in the trigonometric form, we're going to use deMoivre. We're going to use deMoivre theorem to show that this particular expression that represent tangent over phi is true. And then a, b are integers to be determined from our our derivative here. All right. Okay. Now we're going to start off by considering z plus 1 over z here. Okay. Now, one thing I need to clarify here or to review is you can actually substitute the cosine. Before I show you the expansion, you can substitute the cosine here and the sine. So that basically equal to, oh yeah, maybe I will start from here instead. Just as a recap, we know that z plus 1 over z is basically cosine theta plus I sine theta. That is for z. And then for 1 over z, it's basically cosine theta plus I sine theta. The 1 over reciprocal, we can rewrite as -1 here. And then by using deMoivre's theorem, you can refer to my other videos on how the deMoivre's theorem is being derived. You can Here I'm just going to show you the result that deMoivre has already discovered here. So we're going to apply this one here. Basically, that is negative theta plus I sine negative theta here. Okay, and then from here we have cos theta plus I sine theta. The cosine negative theta is always positive, right? Based on the identity, and then this will give you a negative. And then you will notice that the sign, the imaginary terms will cancel. We end up with 2 cos theta. Now that is what we have for z plus 1 over z. Now what if we are going to apply a power 5 onto that? If you apply power 5 onto that, basically we are saying we are trying to apply power 5 here. And then that would give us 32 cosine to the power of 5 cos here. All right, now that's the first one. Now, of course, at this point of time, we need to consider the binomial expansion for this. So I'm going to apply the binomial expansions for this particular expression just based on z itself. Okay, so that will be z to the power of 5. And then after that, 5z4, 1 over z. And then after that, I have C phi 2. I assume C phi 2 would be, let me see here, phi 2, phi 3, phi 4, 2, 10. So it should be 10. So that will be Z3, 1Z square here. And then the other one must be a 10 also. So 10Z square, 1 over Z3. And then after that, I have my 5, 1 over Z4. And then finally, I have my 1 over z5. Now from here, we're going to group the term with power 5, power 4, power 3 together, for instance. All right? Okay, now z5 will be here. And then next, we have our z3. Z3 in this case. So z3 is to 1 over z3. And then after that, I will have my z only. And then I'm going to count how many terms I have just in case I miss out anything. 1, 2, 3, 4, 5, 6. I should have 6 terms. So here 2, 4, 6. So I do have 6 terms here. All right. And then another recap is we have seen this is equal to this, right? But how about z5 plus 1 over z5 in this case, right? Now that one you can refer back to one of my videos on that. So in this case, I'm not going to derive too many of this because it defeats the purpose of the question itself. From here, you don't really need to prove that. All right, from here we can conclude that this is given by 2 cosine phi theta, and then this one is actually 2 2 times 5 here is 10. 10 cosine 3 theta. And then finally this one is 20 cosine theta. And then there you have it. All right, this is the first part of the proof itself. Now, at this point of time, I just want you to know that this entire summation can be written as 32 cosine phi theta. All right, now I'm going to pause here. This is the first section. I'm going to move on to the second section. Then we're going to conclude the proof here. All right, so our next expansion is z minus 1 over z to a power of 5. Okay, now we know that this can be written as, all right, now before that, let me recap one more time. So z1 minus 1 over z is equal to, in this case, we have cosine theta plus I sine theta minus of the cosine theta minus I sine theta here. And then from here, if you simplify that, we will get the 2I sine theta. Now, by applying power 5, we have 2I sine theta to the power of 5. All right. So if I4, just to recap, I4 is basically a 1. I4 is a 1. Oops, sorry. I4 is I2 is a negative 1, sorry. I2 is negative 1. I4 is a 1. And then finally you have that I itself. Okay, so that will give us 32I sine to the power of 5 theta. Now I hope that is clear. And then by using binomial expansions one more time here, I'll get z5 minus 5 z4 1 over z, and then after that I will have my plus z1 z5 2, which is a 10 z3 here. This is a square, so z square here. And then after that I'm going to continue on with another 10 here, z square. This one will be 1 over z3. And then finally I have my, the second last term, I have z. I will have a z4 here instead. And then finally my negative 1 over z5. Okay, by grouping them together based on your degree, this is, let me see here, we have it over here. Yes, correct. Because it's a subtraction, so I will rewrite that as z3 then. Okay, and then after that I have my 10. This is z minus 1 over z. Okay, and then there you have it. Now, as usual, this we can obtain the identity for this. You can refer to my other videos on how to derive this. This is 2I sine phi theta minus of the same thing here. I have 10I sine 3 theta, and then after that I will have my 20I sine theta. Okay, now just to recap on what I have previously. I think I accidentally erased off the other sections, but never mind, just let me show that one more time here. So for the z plus 1 over z5, just to recap here, I do have my z5 plus 1 over z5. Yep, that is correct. And then after that, the same thing go for the second one. So 5 z3 also. And then finally, I do have my z plus 1 over z. And then that would actually yield like what I have is 2 cosine phi theta plus 10 cosine 3 theta, and then finally I have my 20 cosine theta here. Now that's what I have currently. Alright, now I'm going to pause here for a while. Alright, these are the two most important results that I need to um, use it shortly. Okay, now I'm going to pause here, and then I'm going to write down what we have at this point of time. Okay, now I'm going to erase everything, not the entire thing, but the most important result that we are looking for. So we have 32i sine phi theta is or can be represented as 2i sine phi theta minus of 10i sine 3 theta plus 20i sine theta. Now that is the result that I need to use. And then next, the second result that I obtained from the previous question, that is, we know that this is given by 32 cosine phi theta. Is given as 2 cosine phi theta plus 10 cosine 3 theta plus 20 cosine theta. And then by taking the first equation and this second equation, I can sort of perform a ratio on this. So take for instance, I'm going to take 1 divided by 2. By taking 1 divided by 2, and then you will notice that all the I can be cancelled off. So I might as well cancel off all the I first before I divide this. And then the 32 is gone. This can be simplified as sine phi theta over cos phi theta, which is basically just a tangent theta. And then here you will notice that everything can be simplified by 2. I will have this. All right, let's check now once we reach this section here. And then I can conclude that, therefore, this is tangent phi theta. Let me check that, whether everything is correct. Yep, they seems to be in the right place. So therefore, I just need to rewrite this one more time. And then there you have it. We managed to prove this, proven. And then we'll say that where the A is equal to a 5 and then B is equal to a 10 there. And then there you have it. A and B appear to be integer, which fit in the descriptions correctly. All right, so I hope that is clear. We're going to move on to the next question shortly. Our question 5 here. We are given a differential equation. We're going to solve this differential equation. All right. Okay, now A, we need to find the value of the constant k such that y equal to kx exponential negative x is a particular integral of the differential equation. Particular integral of the differential equation. All right. Now, since we are given the particular integral, we might as well just start from here. Since this is particular integral, pi. Now that is what we have. Now the steps to follow, if you are given the particular integral, all you need to do is just differentiate this one time. I hope that you guys are okay differentiating this using the product rule. Now, of course, in this case, it will be kx exponential x. Yeah. And then we're going to perform the second derivative also. Okay, and then that will yield negative k e negative x, and then as usual, this one we have k, not kx here, but ke negative x, and then after that we have the kxe negative x. All right, so I hope that is clear at this point. Okay, now next, all we need to do is just substitute equation 1, equation 2, and equation 3 into the main differential equation. So we're going to substitute all this into here. And then using comparison methods, we hope that we can obtain the value for k in this case. Right? So let's do that. That will be, in this case, I notice that I can simplify this further. So maybe I'll just rewrite that as negative 2k exponential negative x. Let me clean this up. This is exponential negative x. All right, that's what we have. And then subtract off with 2 times the dy dx. So that will be k exponential negative x. And then minus of kx 2 times also. So 2 times kx exponential negative x. Okay, now that is 2 times of that. And then finally plus with the, oops, it's not plus, it's subtract with 3y. And then the y is kx exponential negative x must be equal to 4 exponential negative x. All right. So from here, all we need to do is just simplify as much as possible. Okay, now let me just open up the bracket. Now, if you don't want to confuse yourself, you can remove all the exponential here. For me, I think that is much more easier instead of looking at the exponential. We have 2k plus 2kx minus 3kx is equal to 4 here. And then next, all we need to do is collect all the like terms together. I noticed that these three terms, basically they cancel off each other. I end up with only these two, negative 4k is equal to 4. And then we can conclude that k is equal to negative 1. And then we have successfully answered question 5a. All right, so I hope that is clear. Now I'm going to pause here for a while. We're going to solve the second part to obtain the, I would say, more like specific solutions for this differential equation. Right, now that we have found the particular integral, I'm just going to rewrite that at the side here. We have y is equal to negative x exponential negative x. That's our particular integral. Now next, in order to find the specific solutions to these differential equations A just now, we need to find its complementary function. So to find its complementary functions, we need to work out its characteristic equation first. So its characteristic equation is, usually we will let y be, if you want to recap, usually we will let y equal to ae mx, yeah. And then by differentiating this, substitute inside there, you can actually simplify as, so take for instance, in this case we have dy dx as am exponential this, second derivative as the am square. All right, now it's time for us to substitute this one again back into the first differential equation. So from here, we have the m square ae mx minus of 2 times of this. So 2 times of m ae mx, and then minus of 3 times of y, which is ae mx. All right, and then that would be equal to a 0, because here I noticed that most of the time when you look at this, when you substitute, it's supposed to be equal to 4 exponential negative x. But because we are working out the complementary functions, we only consider the homogeneous equation. So here I like to make a remark here. We are considering the homogeneous equations of d square x squared minus 2 dy dx minus 3y is equal to 0. That is our consideration here. That's the reason why we have this. And then because exponential mx cannot be equal to 0, and then we can simplify that. That is what our characteristics equations would basically look like. And then you can factorize that quite easily. And then from there, our complementary functions will be, I just write down CF here, it's easier to recognize. It's basically AE negative x plus BE 3x there. All right. Okay, and then there you have it. Okay, this is our complementary function. We have found the particular integral. Now we're going to combine both of these together to form a general solution. And then by considering the specific condition, we will be able to solve or obtain the specific solutions to this. All right, so I'm going to pause here for a while. I'm going to rewrite the CF at the side here so that we can use it in a while. It's AE negative x plus BE 3x here. All right, now I'm going to pause here for a while. Right, next we have already obtained its particular integral and the complementary function. Therefore, our general solutions is consisting of its particular integral and the complementary function. Therefore, we have this. All right, now that will be our general solutions. In order to obtain a specific solution, we're going to make use of the conditions given to us. When x is equal to 0, y is equal to half. That's how it read to me. So when x is equal to 0, this part here is 0, and then what we're left with is a plus b is equal to a half. Now that will be our first equation. Okay, let me rewrite these numbers correctly. It looks like different number here, 2. All right, and then next, the first derivative, dy dx. So we need to differentiate this. Okay, that's what we have. And then the same thing when x is equal to 0, dy dx is equal to a half. And then what does that look like? And when you substitute 0 inside, we will have a plus 3b minus a 1 here, and then this is 0 is equal to a half. And then we can rearrange that further, equal to 3 over 2. That will be our second equation. And then by solving both of these, we can solve 1 and 2. We will be able to obtain the first value that I can obtain quite easily. I would say b is equal to, if you add this one up, it's a 2, 4, so 1 over 2. So b is equal to 1 over 2. Because b is equal to 1 over 2, therefore a must be equal to 0. Then finally, our specific solution, right? Or particular solutions in this case, particular solution, or sometimes we call it particular solution, is given as y equal to our a is 0, so only left with b, that is half, e3x minus of x e negative x. And then there you have it. That's our specific solution or particular solution, or sometimes we call that particular solution. All right. So I hope that is clear. I'm going to move on to the next question shortly. All right. Question 6. This is a hyperbolic sine and cosine and tangent. So first part, starting from the definition of the hyperbolic sine and hyperbolic cosine in terms of exponential, prove that this is true. Okay, so we're going to start off from the definition here. We know that sine hyperbolic x is given by this, whereas cosine x is given by this. All right, that is the one that we have. And then all we need to do is prove that this definition is true then. So on the left hand side, you can do this quite easily. So on the left hand side, we have 2 sine hyperbolic square. So that would actually give us the square of this. That will be a quarter a square. And then if you simplify that, that's basically a half ex negative. Okay, and then there you have it. That's the first part there. And then next, from here, if you like, you can straight away prove it from here to this side. So take for instance, we can expand this. That will be e. If you expand that, that will be e2x, and then minus of a 2 plus with e negative 2x here. And then by a bit of rearrangement, that will be e2x plus e negative 2x minus a 1. And then this actually gives us the definition. If you knew that, cos 2x is basically half e2x plus e negative 2x. And then by using that, we can conclude that this is the same as cosine hyperbolic 2x subtract 1. And then there you have it. This is the same as the right hand side expression. Therefore, we have proven this, right? So I hope that is clear. We're going to move on to the second question shortly. Right, now let's take a look at section B. We need to provide a solutions to this first order differential equation. And then we are given the conditions when x is equal to ln 3, the y is equal to 1. All right. Now this is first order. Therefore, I would suggest that you try your best to use integrating factor method. All right. Now we notice that from here. Now for integrating factor, you can also refer to one of my videos on that. So I'll share the link later on. Okay, so from here, our integrating factor, first of all, we're going to find out the integrating factor is basically given by exponential raised to the power of the integration of cotangent hyperbolic dx. All right, now that is the procedure that we use to find integrating factor. And then that is basically the same as, okay, I can write this one down as ESP. It's easier to represent exponential anyway. Cotangent hyperbolic x integration. All right. And then at this point, we might want to consider the integration here. Now I'm just going to consider this integration. Now cotangent is basically cosine hyperbolic and sine. And then you can actually integrate this quite easily by using substitution. All right. Now that is typically if you integrate this using substitution, let u equal to sine x here, you will end up with sine hyperbolic x there. And then therefore these sections will be e to the power of ln sine hyperbolic. And then that would yield sine hyperbolic x. All right. Now I hope that is clear at this point. That is how we obtain the integrating factor. Once we have done that, we're going to use this integrating factor to complete the solutions to the first order differential equation. All right, so I'm going to pause for a while. All right, now we have already found out our integrating factor, which is a sine hyperbolic. Therefore, we can transform this into the product rule form. So we can rewrite this as dy dx. The original form was integrating factor with a y must be equal to the integrating factor with the 4 sine hyperbolic x. Okay, that's how it look like. And then from here, all you need to do is just uh, rewrite all this. This is sine hyperbolic x, y, and then that will be, I think it's better to write this way, or else it'll look a bit weird in this case, or like this. And then this will give us a 4 sine hyperbolic square. All right, and then with a bit of integration, we found that this is the integrations of the hyperbolic sine. Okay, all right, so that's what we have. And then we need to make use of an identity, in this case, for this particular integration. Of course, this is just one of the methods. If you are free or if you have other ideas, you can always try this one out. Okay, now one of the identity that we need to try out will be here. If we can remember the trigonometry identity, for instance, we do have trigonometry identity of cosine 2x is basically equal to 1 minus 2 sine 2 sine sorry 2 sine square x. Now this is the identity that we have from trigonometry. And then there is a rule that we need to follow on how to transform this trigonometry identity into the hyperbolic trigonometry identity. All right. So the rule says that as long as you have a sine square, you have to change it to positive. So from here, the cosine hyperbolic 2x is the same as 1 plus 2 sine hyperbolic. All right. Now that's how it would actually look like. So if I rearrange this a bit more, you will notice that this is the same as cos 2x minus 1. And then that's exactly what we are going to do. Instead of writing that as a 4, I might want to change it to a 2, for instance, so that I can utilize this identity. Then that will become 2, and then the entire thing will become the cos 2x minus 1 dx here. And then integrations for this shouldn't be a problem. That is basically just a sine 2x divided by 2, of course. And then this integration is very easy, it's just x. And then simplifying that, we have sine hyperbolic 2x minus 2x here. Now, of course, at the end of the day, it will be plus c. And then this is what we have. All right. And then finally, we are given that when x is equal to ln 3, our y is equal to 1. All right. So I'm going to pause here for a while. You can check out this answer here. I'm going to rewrite these solutions at the side, and then we are going to work out the value for c, and then we can conclude the solution. right? Right, this is our result that we have obtained previously, and then now we have to figure out what is the value for C by using these conditions. When x is equal to ln 3, our y is equal to 1. So all we need to do is just substitute this one in. And now, of course, it's always best to make use of the definitions for sine hyperbolic here. Now I'm going to write it down at the side one more time if you have forgotten the definition. Okay, this is a definition. We're going to substitute that directly. This is basically just 1. Now, sine x become half e ln 3, subtract off with negative ln 3. Okay, now that's how it look like on the left hand side. On the right hand side, the same thing. We will have e instead of 2, then that will be a 2 ln 3 minus of e negative 2 ln 3. And then finally, we need to put down the 2 ln 3 and then plus a c. So we're going to work out the c. And from here, we have, now if you want, this is basically just 3 and then minus of 1 over 3. This is 1 over 2. Now, I would say that there is a 9 minus 1 over 9 plus a c. And then simplifying that, that is 4 over 3. And then this one is 40 over 9 minus of 2 ln 3 plus c. And then from here, we found that the c itself is basically, let me see here, we have 2 ln 3 subtract off with 3 12, let me see, 28 over 9. And then now we can conclude that the solutions to this is y sine hyperbolic x equal to sine hyperbolic 2x minus of with 2x plus with a c. Alright, so I hope that is clear. We can move on to the next question shortly. Right, question 7. The first part, we are given the integral in, where n is an integer, is defined as such. We need to find the exact value of the first integrand, which is I1, expressing your answer in logarithmic form. So we're going to start with that. Now that is a I1. So I1 basically means 4 plus x squared to the power of negative half. Okay, that's I1, right? And then you will notice that this is typically or can be written as 1 over 4 plus x squared square root. Now, when you encounter such format, it's always good to use like either trigonometry or uh, hyperbolic trigonometry function, right? Now, if you have gone through some of the substitutions methods for integration, you will notice that here you need to make use of the hyperbolic sine or hyperbolic cosine here. So I'm just going to make use of one of them. I think it's easier to use let x be sine hyperbolic theta, for instance. All right, and then from here we can differentiate this quite easily, which will yield cosine theta. Okay, now that should not be any problem. You can readjust the subject. So this is the one that we have. Okay, now we are almost there. From here, I'm just going to consider this one first. You can see that just by considering this, 4 plus x squared Oops, when I notice that when I use these substitutions, I thought that it will works initially. Okay, now you see that when I substitute this one in, I'm not able to sort of factorize out the 4. So I'm still sort of stuck with this particular format. Therefore, with a little bit of adjustment, sometime if you encounter this, that's fine. So with a little bit of adjustment, all I need to do is, instead of using that substitution as sine hyperbolic, you can purposely introduce the 2 sine hyperbolic theta. And then from here, dx d theta is equal to 2 cosine theta. And then from here, we're going to consider this one more time. You can see that 4 plus the square of this, that will be 4 sine square theta square root here. All right. So that's what we have. And then from the identity, we notice that the cosine hyperbolic x minus of sine hyperbolic x here must be equal to a 1. And then therefore, from here, we notice that 1 plus sine hyperbolic square is basically the same as cosine hyperbolic x. Now we're going to make use of that result over here. All right. Now this entire thing can be simplified into, you will notice that this is just a half, and then after you take out the 4, you will have 1 plus hyperbolic sine square, and then that is the same as cosine. That would become 1 over cosine theta in this case. It will become cosine theta. And then there you have it. Right, that's what we have at this point of time. Once you're ready, then we're going to look at I1 one more time. In this form, we're going to replace all the substitutions that we have set up. Now, we know that this has been changed to, this entire thing is here, has been changed to a half 1 over cosine theta. It's been changed to this. And then dx, what is dx? We notice that dx is 2 times of cosine hyperbolic d theta. Okay, here I'm going to leave out the lower and upper boundary first. You will notice that all the thing can be cancelled off. And then at the end, we have just a 1. And then integrating a 1, it's just a theta. Okay, it's just a theta in this case. Then the critical part is here. We are asking ourselves, what is theta in this case, right? So the theta is itself, we can obtain it from here. I'm going to rewrite one more time from here. Okay, so we know that theta is this. And then I'm going to erase off this part first so that it's not very messy. And then from here, you can rewrite your theta as the inverse hyperbolic sine x over 2. Now that is our theta here, right? And then from here we can include. Okay, so from here we can include the lower bound and upper bound. So from here is the same as sine inverse x over 2. The lower bound is 0, upper bound is 3 over 2. And then all we need to do is just substitute this. I'm going to write it down at the side here. So if you substitute this, we will get the sine inverse 3 over 4. Subtract off with sine inverse. Subtract off with sine inverse 0. All right. So that is what we are trying to find here. All right. At the end of the day, we can find out the two of this value. Now, one of the value here must be 0. You can actually enter that into your calculator. Shouldn't be a problem at all. Okay. Now, the second one is this. How do I find this answer here? All right. Now we can actually let this be, we can let this be u. So sine inverse 3 over 4. And then therefore sine u is equal to 3 over 4 here. And then sine u is given by half EU minus negative EU equal to 3 over 4. All right. Now from there you can solve this exponential equation. Yeah, I'm going to pause here for a while. I'm going to show you how to solve it one more time to obtain the integrand of I1 there. This is where we are at. We're going to solve this exponential equation before we conclude the I1. Now, all we need to do is just get rid of this 4. For instance, if you want, that will be a 2EU minus negative u here, and then that will be a 3. And then after that, we want to get rid of the EU. It will be 2u here, and then minus off with 3EU, and then minus off with a 2 here, right? So you can check that on your own, see whether it makes sense to you. And then from here, we can factorize this quite easily, I would say. That will be plus 1, and then EU here minus a 2. Let me check whether that makes sense or not. Yep, it does make sense. And then we know that we cannot accept this result, 2EU plus 1. Therefore, because 2EU plus 1 cannot be equal to 0, therefore EU must be equal to U must be equal to ln 2. And then again, what is U then? What is U just now, right? So because we have represented the U as um, the sine inverse of 2 just now. Oops, sorry, it's not sine inverse of 2, it's sine inverse of 3 over 2. That is from here. Okay, so from here, we have already found our U, which is the solutions to I1, and then our U is ln 2. Therefore, we conclude that I1, which is equal to the integrations of this, must be equal to this one here, 3 over 2, and then this one gives us the U, which is ln 2. And then there you have it, the first answer A here. I hope that is clear. Now we're going to move on to B and C shortly. All right, for B, we are by considering these differentiations or otherwise show that these um, iterative integrations form can be obtained. All right. Now, how are we going to do that? We're going to consider the differentiation here by considering this differentiation. Okay, this is not tough. It looks tough, but you just have to go through that. Okay, we're going to use a product rule. That will be 4 plus x squared negative half n. And then thereafter, I'm going to hold the other one here. If you integrate the second part, it will be half n, and then x there. X will still remain. And then after that, we will have 2x there from the internal bracket. And then finally, we have 4 plus x squared to the power of half n minus 1. That's how it look like. And then we can try to simplify that. All right, now that shouldn't be any problem here. We have nx squared, 4 plus x squared. All right, now this part here, we can further simplify that as half n plus 2 because n plus 2 is basically just this. Okay, and then this is what we have currently, and then I'm going to write it side by side one more time. Okay, now what comes next is very important. Once you obtain this differentiation, we can reverse the process here by applying the integration. So here I'm going to rewrite the integrations directly. Okay, I'm going to put a bracket here with respect to dx. Yeah, the same goal for this part here. It's a differentiation with respect to the axis. Okay, let me clean this up here. So this is a differentiation with respect to dx. The same goal for this one here. All right. So I hope that is clear at this point. And then the integrations is antiderivative of differentiations would only give us the same result. Oh yeah, by the way, I'm going to let me see here. Okay, let me erase this and then rewrite neatly so that you can see clearly what I'm trying to achieve here. Okay, so from here we're going to perform the antiderivative, okay, from 0 to 3 over 2, right? Because that is the one that we want to get in here. And then that will be differentiations of this with respect to dx, of course. And then thereafter, this will be the integrations from 0 to 3 over 2. This 4 plus x squared negative half of n dx. And then after that, the second part will be here. It will be n, so I can take out the n because it's the same thing here. 4 plus x squared negative half of n plus 2 here, respect to dx, from 0 to 3 over 2. That's how it look like. And then this part is quite easy because you reverse the process. Therefore, the answer is just x4 plus x squared negative half of n. And then we are going to integrate that from 0 to 3 over 2. This part here is simple enough also. As you can see, this basically represent in. So this entire thing is in. And then this part here is very important. This part here we can rewrite. I noticed that there's an x squared. So you can purposely write down x squared plus 4, for instance. X squared plus 4 minus 4, or I can say that 4 plus x squared minus 4 like this. You can see that. All right. Now, and then after that, you can further expand that. You can expand this become 4 plus x squared. Right. Now, that will be a plus 1 basically. Right. So it's plus minus 1 plus 1, which is negative half of n. Yeah, that is first one, 0 to 3 over 2. And then thereafter, I have a plus a 4n here. So I have a plus 4n, 4n 4 plus x squared, negative half n plus 2 dx from 0 to 3 over 2. And then that would basically give me in minus of n. This is also in. Yeah. And then finally this part here become 4n. This is in plus a 2. Okay, and then we are almost done. All we need to do is just substitute this value into here. So if I were to substitute this value into here, that will give me 3 over 2. And then I'm going to substitute this one into here also. And then that will typically give me a 9 over 4, 1625. So let me see here. There's 9, 4. So it's 9, 4. So 1625, 4. So anyway, you can turn it upside down. 4 over 25, 1 over 2n. Basically, this is how it look like at this point in time. Okay. Now I'm going to pause here for a while. You guys will be able to figure this one out, because 4 over 25, square root of 4 over 25 is actually 2 over 5. And then that's how we obtain the final part here. 3 over 2, 2 over 5. And then these two can be combined, of course. And then we will be able to reach the conclusion. All right. Okay, I'm going to pause here for a while. You can look at that. I'm going to erase this part just to conclude for you to see how does it look like. Okay, we don't need this anymore. I'm going to conclude this. So I'm going to rewrite this one more time here. We have 3 over 2. This one can be simplified, become 2 over 5, n instead. And then in, of course. This one can be factorized as, well, if you want, you can factorize it as this. Okay. You can purposely change the format so they look like this. This is n minus 1. You can see that it's basically n minus 1 in plus 4n in plus 2. Okay, now I'm going to pause. You can check at this point. And then we are almost done. All you need to do is just collect all the terms on the right hand side and compare with the right hand side. Therefore, if I switch it over, it will have plus 2 must be the same as 3 over 2 here, 2 over 5, n plus n minus 1 in. And then there you have it. That is the proof for section B there. I'm going to pause here for a while. You can check out the solution. Hopefully you're okay with this. We're going to move on to C shortly. Right, let's take a look at C here, I phi, by using this iterative formula. So we will have I phi. So we can start off from n equal to 3. So let n equal to 3. We will have 3 times 4 here, 12. And then that will give us I phi. And then you have a 3 here. And then 2i3. Okay, that's what we have. Now, of course, we can try to simplify this part here. Let me see, 8. Okay, this one is 8, 4, 12. Okay, so we can have here, up to here, we have 12 over 12 over 1, 2, 5 plus 2i3 here, plus 2i3. Okay, that's what we have currently. And then after that, we can start off by having n equal to, now we are interested to get our I3. So we can let our n equal to 1. Therefore, we have 4i3, 3 over 2, 1, plus 1 minus 1 is 0. Okay, so that is a 0 in this case. Okay, so I hope that is clear. And then from here, we can conclude our I3, which is 3 over 20. 3 over 20. And then from this section here, we're going to substitute this one inside here. We have I phi is equal to 12 over 125 plus twice of I3. And then that will give us like 12 over 125 plus a 3 over 10 here. And then finally, we can get our I phi as 1 over 125 and then plus, let me see here, 1 over 40. And then, of course, we can combine both of these together if you want. And then there you will have, let me check the number. There you have the answer as, okay, either you leave it as a fraction or you can leave it as a decimal. So in this case, I'll just leave it as a decimal. If you like, you can leave it as a fraction. So in terms of decimal is 0.033. Now I'm going to pause there. Hope that you guys is okay with question 7. We're going to move on to the last question shortly. All right, welcome back. These are our last questions for this paper, June 2021, paper 23 here. The first part, we need to find the value of A for which the system of linear equation does not have a unique solution. That's our first part. And then the second part, we have a matrix A is given as such. We need to find the eigenvalue of A corresponds to the eigenvector given as such. There's just one mark. And then C, find the matrix P and a diagonal matrix D such that A is given as such. And then finally, we're going to use the characteristics equation of A to find the inverse in term of A here. All right, now I'm going to break this one down into each bite-sized sections for us to work with. All right, so I'm going to pause for a while. All right, the first question was quite direct when they say that does not have a unique solution, meaning that the equations or the matrix, if you were to represent this in the matrix form, okay, so take for instance, if I were to represent this as a matrix form, 18, negative 28, negative 4, negative A, 8, 2, 6, negative 5, X, Y, Z here. All right, now this one can be written as capital letter A here. This I will represent it with X and then this one with Y. And then from here, when they mention that there is no unique solutions, meaning that we don't have an inverse for A. Therefore, we can't really solve for X and Y. So that is what it means there. So firstly, no inverse or the no inverse of A. Or basically inverse of A does not exist. So what will be the conditions for not having an inverse for A then? Therefore, for this to be true, the condition must be determinant of A must be equal to 0. Right? For that to be true, determinant A must be equal to 0. Right? So hopefully that is clear at this point. I'm going to show you how to actually get the determinant in this case. All right, so let me erase this off. I'm going to leave that down there. Now, determinant for A, okay, determinant for A, that must be equal to 0 here. So how do I find the determinant then? The determinant will be, first of all, we can start off from here. Okay, that will be 13. And then right after that, you're going to look at these 4 sets of elements here by using AD minus BC. So we will have 5A here minus of 48. And then for the second set, it is minus. So we have to put in the minus sign 18 here. And then you can actually use a invisible line just to cross 18 and vertically down, then you'll notice that those number that does not cover, we're going to apply AD minus BC here. So that will be 20. That is 20 here minus 16. And then lastly is 28. Same thing, you're going to cross horizontally and vertically. These will be the four elements that we're going to work with. Negative 24 plus 2a here. And then this determinant must be equal to a 0 for it not to have a unique solution. All right, so from here, all I need to do is just finish it off. This is 65a here. And then, of course, this number is quite huge for me to calculate. Let me use a calculator on this. I will have like 624. And then after that, this one is easy here, 72. And then after that, I will have a larger number here, 28 by 24. So I will have like 672 here. And then finally 56a is equal to 0. By simplifying all this, I will have a 9a, of course. And then finally, just let me check through this in case I make mistake. 624 here. Then that will be a positive. Okay, so eventually you get negative 24 equals 0. And then therefore a is equal to 24 over 9. That is typically 8 over 3. And then there you have it. For having an a equal to 8 over 3, the system of linear equations will not have a unique solutions then. All right, so I hope that's clear. We're going to move on to the second question shortly. All right, the second section B, to find out the eigenvalue of A corresponds to the eigenvector. Now, the general format to work with eigenvector and eigenvalue is here. We let A represent this transformation matrix, then it must satisfy this for any eigenvalue and eigenvector, which is given as such. All right. So we do have the A here. We do have one of the eigenvector here. We need to figure out what is its eigenvalue, which is given by the lambda itself. All right. So here I'm going to rewrite this. In this case, it is I'm going to work out AE first. So let's consider as AE. So AE is 13, 18, negative 28, negative 4, negative 1, 8, 2, 6, negative 5. And then we just need to multiply that with the eigenvector. All right, now I don't have calculator at this point, so I'm going to work it out manually. So we have 26, negative 2 then. It must be negative 2. And then next one here, I will have like a negative 8. Negative 8 in 8 is 0. And then after that, the last one, I will have 4. 4 and a negative 5, which is negative 1. And then you will see that this one can be factorized as negative 1, 2, 0, 1 here. All right. Now that look exactly the same as negative 1, whereby this is actually the eigenvector. And then by comparing that to the original format for eigenvalue and eigenvector, we will notice that the eigenvalue must be equal to negative 1. This will be the eigenvalue correspond to eigenvector 201 here. All right, now that's it. It's just one mark. I hope that is clear. We're going to move on to the next section shortly. All right, next one, C. We're going to work out the diagonal matrix D and its model matrix P, which represent all the eigenvector. It's a collections of eigenvectors matrix, whereby diagonal matrix represent the collections of all the eigenvalues. One of the eigenvalues that we have already obtained is lambda equal to negative 1. Now we're going to figure out the rest of the eigenvalues. All right. Now to do that, I'm going to rewrite the equations for that relates the eigenvector and eigenvalues together. There's this. And then you can rearrange this so that you have this equal to 0. And then from here, we can factorize that. And then finally, to solve for this, the determinant of a minus I lambda must be equal to 0 to yield infinitely many solutions here, right? So a minus I lambda. So basically, it means the a, this is the a, and then subtract off with lambda. Yes, I'm going to use the modulus sign just to represent the determinant equal to 0 here. And then that would typically give us a lambda here, 18, negative 28. And then after that, you have your negative 4, negative 1 minus lambda. And then finally, we have 8. We have 2, we have 6, we have negative 5 minus lambda. So the determinant must be equal to 0 here. Now I'm going to work out the determinant now. We have 13 minus lambda multiply with, okay, basically it's like this. Multiply with this and AD minus BC. But because both are negative, usually I will just convert them to positive. It's easier to work with in this case. Minus of 48. Now that's my first one. And then after that, I need to subtract off with the 18. All right, 18 AD minus BC. That would be same thing. This multiply with this. That will be 4, 5 plus lambda. And then let me see here. 5 plus lambda minus of 16. And then finally, I need to add them up to the last one, which is negative 28. Now that will be negative 24 plus 1 plus lambda multiplied by 2. And then the entire thing must be equal to 0 here. All right. Now, for this, it shouldn't be a problem at this point. Okay. So all you need to do is just finish off this particular expansion here. All right. So I'm going to pause here for a while. You guys can work it out. I'm going to write down the final answer directly. All right. Right, guys, after you have expanded this, right, I'm just going to take shortcut after work out the solutions. You should be able to reach this conclusion here, assuming that you expand everything correctly. We should have something here, and then that will be a 3 and a 5, right? And then eventually you will be able to find out its eigenvalues. All right, so those are the eigenvalues that we have obtained, right? So I hope that is clear how to get the eigenvalues. And then what is the significance of getting eigenvalues then? This would actually give us the diagonal matrix D. So the diagonal matrix D is written as, now since we have the first one as negative 1, so therefore I'm going to list that down as, list down all these eigenvalue diagonally, and then the rest should be a 0. And then there you have it. We have already obtained the eigen values, and then we managed to use the eigenvalues to produce its diagonal matrix at this point, right? So I'm going to pause here for a while. Next, I'm going to work out all its eigenvectors so that we can build the model matrix P. Okay, lastly for section C, we're going to work out all its eigenvector that corresponding to these two, 3 and 5. So let's start from 3 first. For the eigenvector that corresponding to 3, we have 3e here. And then the same thing, we're going to rearrange this as a minus 3i here. Okay, now that's what we have. And then from here, all you need to do is just simplify that. So we have a 13, 18, negative 28, 4, negative 1, 8. And then we have 2, 6, negative 5. And then subtract off with 3, 0, 0. Okay, so that's what we have currently. We do have E as the XYZ in this case. Is equal to 0, 0, 0. That's how it actually look like. So if we were to try to simplify this one here, we will get a 10, 18, and then negative 28. Same thing, negative 4. That will be negative 4. And then finally we have 8. We have 2, we have 6, we have negative 8 here. All right. And then next, all we need to do is just you can do a bit of simplification if you want. All right. So from here, all you need to do is just solve this particular matrix equation. I'm going to show you how to do it maybe using algebra. I think some of you are more familiar with algebra. Of course, there's another methods that my students do learn about, which is using row reduction method. So I'll try to see whether we have time. I'm going to show you both of them. All right, so I'm going to pause here at this point. I'm going to write down um, the metrics that we have, and then I'm going to work out the solutions to this. All right, so that is typically 10. I'm going to write that at the side here. Negative 4, 18, negative 28, 8, and then negative 8. All right, this is x, y, z. This is equal to 0 here. I just mark it down as it is. Okay, let me clean this up. Okay, so from here, I'm going to show you how to use the algebra method to obtain the eigen vector. All right, so we can actually write this one down back. We can write this matrix form back into algebraic form, which is this. Z is equal to 0. If you like, you can simplify everything by 2, for instance. Okay, this is sort of like our first equation. Then the second equation, so you have 4x minus 4y plus 8z is equal to 0. And then you can also simplify that if you like. So that will be plus a y minus 2z equals 0. That will be a second equation. And then the last one, you have 2x plus 6y minus 8z is equal to 0. We can also simplify this. Let me see. There must be numbers that I accidentally mess up just now. All right. So let me check back one more time. If I were to simplify this, right, I actually end up with this part here. So this is not what I want actually. So somehow I know that there's something wrong with this. So just let me check one more time here. I have 13. This for checking purpose. Like in the exam, under exam conditions, very pressure. Okay, so never mind. So just check one more time for the eigenvalues of 3. So 3, 0, 0, 0, 3, 0, 0, 0, 3. Okay, that is a 10, there's a 18, negative 28. Yeah, everything is correct. And then after that, I have negative 4. This is negative 4, so it's 8. That is not wrong. The next one is 2. Yeah, let me see. It's a 2. Yep, it's a 2. It's correct. 6 is correct. And then after that, this is negative 8. Okay, I think there's nothing wrong with this at this point. So, so from here, all we need to do is just finish solving this. So take for instance, at this point, I'm going to solve. You have to anchor one of them. So take for instance, we anchor this part here, and then we're going to solve the rest based on this. So I can say that I'm going to take the um, equation number 2 times 5 times minus of equation number 1, for instance. So I'm going to take this 5 times, subtract off with this. I will get, of course, there's no more x. And then I have 5 times negative 4y. I have 5 times here, negative 10 minus this, so it become 4z equal to 0. And then I can further simplify this as y minus z equal to 0. That will be my fourth equation. And then at the same time, I can take like, since I anchor this one, so I'm going to solve that with number 3. I will say that I'll take equation number 3 times 5, subtract off with equation number 1. So that will eliminate the x. And then after that, I'll have 5, 15, then that will be a 6y. And then 5, negative 20 with this is negative 6z equal to 0. And then I will be able to reach this conclusion here. Now it's very important to get 4 and 5 to be exactly the same, right? So from here, you can let z equal to any variable, or we say that is a free variable that are real. Okay, because z is equal to t, we know that from equation number 4 or 5, y must be equal to t. And then because y is equal to t, we can use um, any one of the equations. So take for instance, we can use back equation number 1, for instance. From equation number 1, we have 5x equal to 14 z, which is t, minus of 9y, which is 9t. And then from here, we notice that that is actually a 5t. X is also equal to t. And then the solutions or the eigenvector is given by x, y, z. Don't forget that, as I mentioned before, the eigenvector is actually x, y, z. What is x then? X is t. What is y is t. What is z is also t. Therefore, you can um, factorize everything out, and then usually we refer this one as the simplified, or the it's the same as the eigenvector in this case. So we have already found the eigenvector that corresponding to lambda equal to 3. That is 1, 1, 1. Okay, so I hope that is clear at this point. All right, so I'm going to pause here. I'm going to write down all the information that we have currently. All right. The second method is to work out the eigenvector that corresponding to eigenvalue 3. We can use the row reductions methods here. So I'm going to show it to you how to use the row reductions method. This is the one that we obtain from the eigenvalue 3 here. Okay. Now to use a row reduction, we're going to rewrite this as such. Negative 28. All right, usually we will write that down as the, let me see here. Because the result is 0, so I'm going to write down here is 0, 0, 0. 0, 0, 0 is the right hand side result. So I'm going to write that down as an augmented matrix. Right? And then I'm going to perform the row reductions operation, which is very similar to the algebraic operation. Okay, so from here, now from here I can simplify everything first. So just like what I did for my algebra, so I can simplify everything here. Let me clean it up. So if I were to simplify this, just like how I did it just now, so I'm going to divide everything by 2, for instance. This one I'm going to divide by -4, and then that is by 2. Okay, this is what I have currently. And then at the end, all I need to do is perform some row operations here. I'm saying that R2 is can be obtained by taking the R 5 times of R2 minus R1, for instance. And then for my R3, I'm going to say that I'm going to perform 5 times of R3 minus of R1 also. Exactly the same as how we did it algebraically. So therefore we have 5 -14, and then that would yield a 0, of course. And then that is 5 minus -4. 5 -10 is a 4. And then after that, repeat that for the same one. 5 is a 0, 15 is a 4. Um, then this one is 20 is 20 is a 6, is it? Let me try to check one more time. 20, yeah, 20 I get 6. There's something wrong here. Just let me check one more time. 5, 10 minus is a 4. Yep, correct. And then the other one is 5 subtract with this. I will get 0, 15. Oh, it's a 6. I think I made a mistake here. This part is a 6. So this is 6. And then after that, if I do the last one, I will also end up with -20, -6 here. And then the same operations we have here. Okay, now once we reach over here, you will notice that this one can be simplified further, and then that will give us 5, 9, -14, 0, you can say 1, -1, and then 0, 1, -1 also. And then finally, we can simplify the last row there by saying that R3 can be obtained by R3 minus of R2. And then that will yield 5, 9, -14, and then 0, 1, -1, and then 0, 0, 0. Okay, once we reach this section, now we are going to perform the same routine as what we did. So I'm going to write down the routine over this side here. We're going to say that let z equal to t here. And then we notice that from here we can convert back to algebraic form, which is y minus z is equal to 0. Therefore, we notice that the y is also equal to t. And then by substituting this one back to 5x plus 9y minus 14z equals 0, we also found out that, like before, x is equal to t. Therefore, the eigenvector corresponds to eigenvalue 3 is equal to 1, 1, 1. Okay, so I skip some of the formality here. Right, I'm going to pause there. Hopefully this is clear to all of you. And then I'm going to finish off the last eigenvector corresponds to 5. Right, now we're going to look at the eigenvector correspond to eigenvalue 5. So lambda equal to 5 here. We will have 18 minus 28 I skip some of the former step, which look more or less the same. Okay, This one will be x, y, z here is equal to 0. Okay, yeah. And then once I simplify that, I will get 8, 18, negative 28. I'm going to rewrite this in the augmented matrix form. So that will be like 8, 18, negative 28. This one will be negative 4, negative 6, 8, and then 2, 6, and then that is negative 10 here. I'll write down in the augmented matrix form. And then of course we can simplify that. So I'm going to simplify that by let's say a 2, 4, 9, negative 14. And then this one I can simplify by negative 2 also. So 2, 3, negative 2, that is negative 4. Simplifying by 2 is 3, negative 5 here. And then right after that, I'm going to perform the row operations here, R2, R3. I'm going to take like 2 times of R2 minus of R1. And then this part here, I'm going to take like 4 times of R3 minus R1. And that will give me 4, 9, negative 14. And then this one will be 0. So 2, 2, 6, negative 3. 2, negative 8. That will be a 6. Then finally we have the 4 times is 0. 12 is 3. Negative 4, 20. So 20 is negative 6 there. 0, 0, 0. Right? And then once you simplify the last one, just let me show you the last part there. 6, 0, 3, negative 6. Okay, now for this one, all we need to do is just take the R3. We can take the R3 plus R2, and then that will give us 4, 9, negative 14, 0, negative 3, 6, and then 0, 0, 0. And then from here, we're going to conclude the solution. We can let z equal to t, just like before. And then from the second row, you will notice that it's negative 3y plus 6z is equal to 0. And then therefore from here, our y is actually equal to 2z, which is 2t. And then from the first row there, we have 4x plus 9y minus 14z is equal to 0. And then all we need to do is just substitute all this into here. Let me see what do we have. 4x is equal to, this one will be 18t. 18t, that will be 4t, so minus 4t here. And then therefore, your x is equal to negative t. And then we can conclude that therefore, the eigenvalue that corresponds to eigenvector that corresponds to eigenvalue 5 is given as negative 1. And then this is 2. And then finally, we have a 1 here. Now that will be the eigen vectors that we have. All right. And then at the end, I'm going to collect all the eigenvectors that corresponds to negative 1, 3, and 5. We're going to finalize the matrix, model matrix P shortly. Right, finally, I have listed down all the eigenvector that corresponds to the eigenvalue. This eigenvector corresponds to eigenvalue negative 1 that we obtained in the previous section. This is the eigenvector that corresponds to eigenvalue 3, and then finally this is eigenvector corresponds to eigenvalue 5 here. All right, and then how do we finalize the P? Now, therefore, before that, I'm going to write down the diagonal matrix one more time, just as a reminder or reference in this case. So it's a matrix that consists of all the eigenvalues diagonally, and then whereby the model matrix P is a collection of all the eigenvectors arranged in the order based on the eigenvalues. So this is our model matrix. So we have 1, 1, 1, and then finally negative 1, 2, 1 here. And then there you have it. That's the answer for C there. All right, so I hope that is clear. We're going to move on to the last one directly from here. Okay, so I'm going to erase all this. And then you will notice that I keep one of the equations over here because I need these equations for to find the characteristic equations of A to find this, right? Now, in the exam, if you're running out of time, this particular equation is actually known as the characteristics equations that we have already worked out from the previous sections when we key in determinant I lambda is equal to 0. And then after we simplify, this is the one that we have. And then we can call this P lambda here. It's a function of lambda. And then we can replace the lambda with the matrix A. Okay, bear in mind here, I did not provide any particular proof as to why we're doing this. I'm just showing you the procedure to obtain the inverse using a Cayley-Hamilton methods and with the help of characteristics equation, right? Okay. Now that will be equal to a 0. From here, if we are interested to obtain the inverse, all we need to do is this. You can actually move the rest of the matrix A to the other side, and then this is what we have. We just leave the number on one side like this, and then you can multiply the inverse both sides like this, and then that will give us 8, of course, 8i basically, and then this one will be A. And then therefore we say that the inverse is actually 1 over 15 of 8i. 8i basically means 8 subtract off with A. Okay, so our A is 13, 18, negative 28, negative 4, negative 1, 8, 2, 6, negative 5. Okay, let me see whether I can work this one out. This one will be negative 5, negative 18, and then 28. Here I will have a 4, and then this is a 9, and then finally it's negative 8. After that I have negative 2, negative 6, and then finally I have 13. Alright, now that's how we obtain the inverse matrix A. Okay, so use the characteristic equation of A to find the inverse of A in term of A. Okay, in term of A, basically we have already answered that question over here. I think I overshoot a bit just to show you that we can use this equation in term of A to obtain the inverse with all the numerical values here. All right. So lastly, I would like to take this opportunity to wish everyone who are taking further maths best of luck. Just read the question properly and then tabulate it correctly. All right. Until I see you again, most probably I will produce another video on mechanics and statistics to help you guys to go through the last two paper there. All right. Until I see you again, best of luck, everyone.